Imagine trying to map every single tree on Earth. I mean, not just forests, but individual trees, where they are, how big.
Yeah, their exact shape, almost.
Exactly, and why bother? Well, think about it, trees are crucial, right? Climate change, wildfires, biodiversity, carbon, everything. Keeping tabs on them individually is becoming super important.
Mm-hmm. And traditionally, getting that kind of really detailed data, it's been, well, incredibly slow and expensive.
You mean people actually going out there?
Yeah, ground surveys, sending teams out to literally measure and map trees one by one. It's good work, essential even, but you just can't cover enough ground that way. The scale is overwhelming.
Right, so that's where technology comes in, or the promise of it anyway.
Hmm.
Using pictures from planes or satellites, aerial imagery, and then getting AI, machine learning, to analyze them.
Precisely. We've had AI models for finding trees for a while, things like Deep Forest or Detect Tree 2, and they're useful, definitely. But they have this one big drawback.
Yep.
It basically comes down to the data they learn from. These models, they're usually trained on quite specific, often kind of small sets of hand-labeled tree pictures from certain places.
So you train it on California trees.
And it works pretty well in California, yeah.
But take that same model to, I don't know, a rainforest in Malaysia.
And it can really stumble. It doesn't generalize well, as they say, to new places or maybe different types of trees it hasn't seen before. Creating that specific labeled data for every single forest type everywhere, that's the bottleneck. It's hugely time-consuming and costly.
Okay, got it. And that sets up the main question for this deep dive, doesn't it? Can this new type of AI, this model called segment, anything Model 2, SAM2 for short, can it overcome that?
That's the core idea. We're exploring how SAM2 did when they tested it for tree mapping in what's called the zero-shot way.
Zero shot meaning no specific training on trees beforehand.
Exactly. Using the model pretty much straight out of the box on tree images it's never encountered in training. Could it just understand what a tree crown is and outline it?
That feels like a big leap. Because the need for this data, individual tree data from the air, it's just growing, isn't it?
Oh, absolutely. Ecologists need it for forest health, climate scientists for carbon modeling, wildfire folks for fuel mapping, conservationists. The list goes on. And the old methods, like we said, just can't keep pace.
And the previous AI, while helpful, hit that data wall.
Right. Those models, like Deep Forest and Detect Tree 2, they're often based on CNNs, convolutional neural networks. They learn visual patterns.
Okay.
They learn what a tree looks like from the specific examples you feed them. Deep Forest learned from neon sites in the U.S. Detect Tree 2 learned from data in Malaysia and French Guiana. So they're good there.
But not necessarily everywhere else. Okay, so that's the problem setup. Limited old methods, data-hungry previous AI. Now let's properly introduce SAM2. What makes it different? Why the hope?
Well, SAM2 is one of these new foundation models. Think of it like a really powerful general-purpose AI that's been pre-trained on just a massive amount of diverse data. Its job, understanding and segmenting stuff in images and videos.
Segmenting, meaning, drawing the outline.
Precisely. Its real power lies in being promptable. You give it an image, and then you give it a prompt to maybe click a point on an object or draw a rough box around it.
Or maybe even type something.
Sometimes, yeah. And based on that prompt, it generates a really precise outline, a segmentation mask of the object you pointed to.
Wow. So it wasn't trained just on trees, but on everything. Pictures of cats, cars, buildings, landscapes.
Pretty much. A huge, diverse data set. So it's learned a kind of general visual understanding of what objects are and how they separate from their background. It uses a different architecture, too, called a transformer, similar to those big language models people talk about.
And that massive general pre-training is the key to why it might generalize.
That's the hypothesis, yeah. It hasn't seen specific labeled tree data from, say, California, but it's seen so many shapes and boundaries, the idea is it can apply that general knowledge to figuring out a tree crown.
And the big test here was that zero-shot idea, using it without any extra tree training.
Yes, that was the exciting bit. And the researchers looked at its zero-shot performance in two main ways.
Okay, what was the first way?
The first was just using SAM2's built-in automatic mode. It has this feature called an automatic mask generator.
Okay.
You basically tell it to automatically find and segment all the objects it thinks it sees in an image. It sort of samples points across the image and tries to segment whatever's at each point.
So you just let it loose on the aerial photo?
Well, almost. Aerial photos are huge, so they had to run it on smaller patches and then do some post-processing to combine the results. But yeah, it's SAM2 trying to find everything on its own, hopefully including all the trees.
Okay, that's method one, fully automatic. What was method two?
Method 2 was called zero-shot transfer, And it leveraged SAM2's promptable ability. This is really interesting.
How did that work?
Instead of just letting SAM2 run wild, they first ran an existing tree detector, like Deep Forest. Deep Forest isn't perfect, but it gives you rough bounding boxes where it thinks trees are.
Right, sort of general areas.
Exactly. And then they fed those bounding boxes from Deep Forest to SAM2 as prompts.
Ah, so it's like saying, hey, Sam2, Deep Forest thinks there's a tree roughly here. Can you draw the precise outline for me?
You got it. It's a clever way to potentially blend the strengths, the specific tree-finding knowledge, even if imperfect, of Deep Forest with the powerful general segmentation skill of SAM2.
Okay, two interesting approaches. How did they actually test them? What kind of images did they use?
They used a few different data sets. For testing that crucial generalization ability, they used images from a place called Emerald Point in California.
And the key thing.
The key thing is none of the models, not SAM2, not Deep Forest, not Detect Tree 2, had ever been trained on data from Emerald Point. This is a completely unseen environment for all of them.
A real test, then.
Definitely. And they even threw in some tricky images with oblique angles looking at the trees from the side, not just straight down, which can be harder for models trained only on top-down views.
Okay, Emerald Point for generalization. What else?
For more direct quantitative comparisons, like getting actual performance numbers, they used two other data sets. One was the Neon Tree Evaluation dataset.
Neon N, that sounds familiar.
Yeah, because Deep Forest was trained on neon data. So this was testing zero-shot SAM2 against Deep Forest performing on its home turf, so to speak.
Okay, fair comparison.
And they also used data from the Detect Tree 2 dataset, which comes from Malaysia. And again, the Detect Tree 2 model was trained on that data. So similar idea comparing zero-shot SAM2 against a specialist model in its known environment.
Right, so you've got SAM2 going in cold against these specialized models that have home field advantage on those benchmark data sets. So what happened? How did SAM2 do, especially on that new Emerald Point data?
Okay, first, the visual results from Emerald Point, the generalization test. This is where SAM2 apparently looked really impressive.
Yeah.
The researchers reported that visually, SAM2 did a great job segmenting trees accurately, even smaller ones, across different forest densities. And crucially, it seemed much better at handling those sideways oblique views compared to Deep Forest and Detect Tree 2.
So the existing models struggled with the different camera angles.
It seems so. They might have been too accustomed to just seeing tree crowns from directly above in their training data. SAM2, being more general, seemed more robust to that change in perspective.
Wow, okay. So visually, on unseen data, very promising for generalization. What about the hard numbers on the benchmark data sets, Enon and the Detect Tree 2 one?
Right, the quantitative. So they use standard metrics, average precision and recall, with a specific overlap threshold called IOU 0.4.
Okay, precision and recall. How did SAM2 score?
When using SAM2 in that fully automatic zero-shot mode, just letting it find things itself, its precision was, well, relatively low. It scored 0.17 on Neon and 0.16 on the Detect Tree 2 dataset.
0.17 doesn't sound great. Why so low?
The paper suggests it's because SAM2 in that automatic mode tends to over-segment, meaning it might break a single large tree crown into several smaller segments. Or it might segment a bit of the background along with the tree. So you end up with more predicted segments, more bounding boxes, than actual trees marked in the ground truth data. That drags down the precision score.
Okay, so it's a bit trigger-happy, finding lots of little bits rather than one clean tree outline sometimes.
Kind of, yeah.
Yeah.
But, and this is really important, its recall scores were actually pretty good, comparable to the specialized methods. You got 0.41 recall on Neon and 0.65 recall on the Detect Tree 2 dataset.
Recall. Remind me what that measures again.
Recall tells you what proportion of the actual trees present in the ground truth data were successfully detected or segmented at all by the model.
Okay, so even if SAM2's automatic outlines weren't perfect or it over-segmented, it was still finding a decent chunk of the real trees that were there.
Exactly. It's clearly detecting the presence of trees quite effectively, even zero-shot. Its ability to find them is strong, even if the automatic segmentation needs refinement.
How did that compare to the others, like Deep Forest on Neon?
Well, Deep Forest, which is trained on Neon, got 0.61 precision and 0.76 recall on Neon. So higher precision, higher recall, but it knew that data. On the Detect Tree 2 data, Deep Forest got 0.34 precision, 0.60 recall.
And Detect Tree 2?
Detect Tree 2, on its own data, got 0.40 precision and 0.72 recall. On Neon, it got 0.25 precision, 0.50 recall. So you see SAM2's zero-shot recall of 0.41 and 0.65 is definitely in the same league, which is impressive given it had no prior training for this specific task.
That is interesting. It suggests the raw detection capability is there, even if the automatic outlining isn't perfect yet.
And what about that second method, the transfer one, using Deep Forest's boxes as prompts? Did they give numbers for that?
They didn't put specific precision recall numbers for that combined approach in the main table, but they showed visual examples.
And what did those look like?
Really promising. The visual suggests that taking those rough initial detections from Deep Forest and feeding them into SAM2 as prompts leads to much cleaner, more accurate segmentation masks around the trees.
So it refines the output significantly. It appears to, yeah. It points towards this powerful synergy. Use a domain-specific model maybe to get you in the ballpark, then use a foundation model like SAM2 for the detailed outlining.
Okay, let's try and wrap our heads around this. What's the big takeaway message from this exploration of SAM2 for mapping trees?
I think the main point is that SAM2 shows really strong potential for zero-shot generalization. It seems capable of mapping individual trees across different kinds of forests, different conditions, even different camera views, potentially without needing new, costly training data for every location.
Which tackles that huge data bottleneck we talked about at the start.
Exactly. Now, the pure automatic mode, as we saw, has limitations right now, particularly that tendency to oversegment, leading to lower precision compared to models trained specifically for that area.
But its ability to find the trees is still strong.
Right. The recall is good, and its ability to take prompts, like the bounding boxes from other models, opens up really interesting possibilities for combining strengths.
So it's not necessarily about SAM2 replacing everything overnight, but it represents a new approach.
Absolutely. Applying these large pre-trained foundation models look like a really promising direction for remote sensing and Earth observation in general. They offer a path towards better visual understanding at scale.
And they can work with existing tools, not just against them.
Precisely.
Yeah.
They can complement specialized models, potentially making the whole process more adaptable and efficient.
That is genuinely exciting. The idea that these powerful general AI models could help us finally get a better handle on mapping the world's forests, tree by individual tree. It feels vital, especially now with climate change and everything else.
It really does. It's fundamental research with potentially huge practical implications.
It leaves me thinking, if foundation models like SAM2 can learn to generalize this well for finding something as complex as trees from the air, what other really tough environmental monitoring tasks could they help with? Tasks that right now are bogged down by the need for massive amounts of manual data labeling. What else could this unlock?